battery, sodium battery, you know, those kind of things.
Okay. Thank you very much. So thank you again. And then we go to our next speaker, also the last speaker of this morning session. So the last speaker will be from Professor Nao Shuping. Professor Nao is the chair professor and the head of Department of Applied Physics in Hong Kong Polytechnic University. He is also the director of the university research facility in materials characterization and device verification. Professor Nao is a fellow of the American Physical Society. He has published over 400 journal papers with over 22,000 citations. Professor Nao's current research focuses on the nanomaterials and energy materials, particularly the synthesis of 2D materials on several for several applications such as optoelectronics, electrocatalysis, and energy storage applications. Today, Professor Nao will share his recent research on the carbon dioxide electroreduction. So, Professor Nao, please.
All right, thank you, Jamil. So you can see the slide, right?
Yes, we can see.
All right, okay, thank you. Right, this morning there's several speakers already cover quite a wide range of the CO2 reduction. I think in the first session, the first two speakers cover quite a lot of area for the CO2 to CO, and then they talk about this membrane-electrode-assembly type of scale-up type of process. So today I try to focus on the CO2 reduction just to C2H4, this ethylene process, and also try to mention a little bit about. Right, the slide is going, right? Okay, so try to cover a little bit about this, what are the major challenges, although some of the speakers this morning already mentioned. We'll just focus on the basically on the system level problem. And then we will introduce our approach, how to tackle some of the major challenges for the electrocatalytic CO2 reduction, especially for C2H4. Later on, I will tell you why we are interested in the C2H4. And then because of the scale-up process for the MEA, we also demonstrate we can stack several MEA together to increase, or to make it scalable, and to further increase the Faradaic efficiency or energy efficiency for this CO2 reduction process. So I don't think I need to tell a lot. The previous speaker, Professor Zhang, has already mentioned quite why the reason why we need to reduce the CO2. This is some of the images talking about the yearly CO2 reduction in a gigaton kind of level, and talking about the the monthly CO2 concentration. They all going up, and for the whole time, how it affect the global mean temperature and so on. So so there's always there's an urgent need to find a way to reduce the CO2 reduction, and different countries talking about have this carbon neutrality policy set that, I mean, even in China they said that 2050 or even 2060 can reach negative carbon. So this is something we are actually focusing on. Basically, if we can use renewable energy for the CO2 reduction, And then there's another way that people can capture the CO2, from the electrical plant or some other area that they will have a lot of CO2 emission. Then we can actually capture it and then purify it and use it for this CO2 reduction process. So we mainly will use this MEA, membrane-electrode-assembly type, because it is a scalable process. We can actually make it in the future. Hopefully, it's more close to a practical use. And then after that, because depending on the catalyst we use, it can cover different fuels, gas phase, or CH4, C2H4, CO, or ethanol, all this. Okay, there's so this can be used for direct fuel, make it to gasoline, and then the other part can also make it to chemicals, different kind of chemicals, and later on for plastic, for cosmetic, for all these kind of chemical, it also needs that. So this is our thinking. If we have a very good MEA system, or we have a very good catalyst, it can have have a very high selectivity for certain field. In this presentation, we only focus on C2H4. Okay, then there will be a lot of application. Okay, so why we are interested in the ethylene C2H4? One of the reasons, there's the demand is the global demand is really high. They talking about the market forecast grow there by about 7% per year. So the market value just for 2021 is 234 billion US dollar. Okay, and then another few years later they will increase to about 300. Okay, so this is a very important chemical. On this part, you can see it can make a lot of polymer because it's a precursor or source material. It can make a lot of aquatic type of hydrocarbon, PE, PET, and PVC, PS, and all this. Okay, even fiber and other organic chemical. So if we can find a catalyst, it can convert CO2 to ethylene for very high Faraday efficiency. There will be a lot of value there. So that is also the reason we are interested in this product. So there's certain challenges. Of course, you need to find a catalyst. It's a very high selectivity, because I think in the previous speaker mentioned, CO2 reduction process is very complicated. It could generate many type of products. And another thing is at the fast reaction kinetic. Okay, you need high current density, and of course a low reaction over potential. Okay, although we are using renewable energy, it may not be very critical. If we, of course, it's lower would be better. And for the stability, I think nowadays also really challenging. If I think the only MEA is much more closer to the practical use. If we can, put the process in MEA rather than in flow cell or H cell, it's very difficult to scale it up. And then the other part is about the membrane. If you can improve the membrane performance, this especially for the anion exchange membrane, we certainly can improve the stability. But the other very important challenge is this carbonate formation or crossover in the normally in the electrolysis cell. They will either use alkalis or neutral type of electrolytes. So that make it very difficult to stop the crossover and stop this carbonate formation, because once the carbonate formation, it will block the cell, and then it will cause flooding, and then eventually it will shut down your cell. Okay, so you make the stability of the cell become very poor. So so in terms of the selectivity, so copper is one of the electrocatalysts can have a very good selectivity for C2H4. So this is some of the other people work. They use basically copper and targeting for C2 type of product, like ethylene type of product, and they can get different quite a good reasonable type of Faraday efficiency for C2. They can easily go to 80% for C2. But C2, they also not just C2H4, so yet they have to later on find a process to, you know, purify or isolate all these liquid or gas fuels, all this. So so there's still quite a lot of interest to increase the so-called selectivity further. Of course, it's higher the better. And some of the thing for the C2H4 can be up to 70%. This is the work for the using graphite, copper, and then the P2Fe copper material. They can reach that copper level. Okay, so the other process, the other problem about is crossover, just now we mentioned. So there's different approaches to tackle the crossover problem. One of the way is you use a very strong acid, okay, rather than using alkalis. Then you can actually reduce, you know, because the acid can actually accelerate all this carbonate formation. But the C2 Faraday efficiency for that kind of approach is only about 40%. Okay, and the single pass CO2 utilization is about 77%. So the other approach is about using a pulse, okay, for C2. As this is not exactly for C2H4. This process for CO, but it's introduced some new idea. They talk about they have to use minimize the alkalis, and then flustered with water for a certain period of time, and then they can reduce the formation of the carbonate. Okay, so eventually they can increase the stability for the reduction for CO to close to 200 hours, with the C2 Faraday efficiency grow to 80%. So based on this work, we are thinking, you know, we have to really find a material or a catalyst with really good Faraday efficiency for C2H4. So this is our approach. First, we need to find a material. They have certain feature that they can improve the catalytic activity. So some of the feature is they may be stringed, okay, and also with smaller coordination number on the surface, so that it can improve this catalytic performance. Okay, so for our case, we focus on the C2H4. We use MEA cell. So the typical cell approach is, we have O2, CO2 input, and then C2H4 come out, and then there's different electrodes, membrane. This is the standard type of MEA cell. Okay. So the first one we found a way that we can create, use a quite simple method to make the so-called step-facet-rich copper nanoparticle. So we basically use a solution method, okay, 80 degrees with the copper-based stock solution injected together with some organic solution, ODA, TOP, and OLA, all this, okay, so about 200 degrees. Then we can create these nanoparticles. We call it a step-facet-rich nanoparticle. Later on, we will have some other explanation why we actually call it FF copper. Okay, we have done a series of characterization. We found this nanoparticle, the surface, they contain many step facet, okay, or step, stacking fault, so-called. So depend on how you call it. And this kind of surface morphology is very good for CO2 reduction, and also can improve the Faradaic efficiency for C2H4 product. So from the TEM, we can see all this stacking fault, and there's a fast flow type of trim boundary as well. It depend on which location you look at it. And then if we go into even further fine structure analysis, atomic version of the TM, you can see all this structure. There are different dislocation, boundary, stacking fault, all this kind of material properties features on our catalyst. So later on, we found that this catalyst is very, very good for CO2 reduction with very high selectivity for C2H4. Right. So we also did some analysis on the tensile string using the TEM, and we can identify the stacking fault, the string, and the low coordination number at the edges, and some of the string analysis, the wet part, you can see some of the region for the particle. The string is relatively high compared to other region. Okay, so that also tells us, our catalyst copper nanoparticle is with a certain percent of tensile string, and certain region with a low coordination number. Both factors are very important to increase the catalytic performance. Okay, because of this abandoned type of stacking fault. So later on, because our at deposited copper have a pretty good conversion reduction, for C2H4. Later on, we actually try to anneal them, try to see how the annealing effect, because normally the annealing will heal all this stacking fault and increase the coordination number. So that means that if after annealing the catalyst performance become poor, then we know that this is a very important factor for the electrocatalytic properties. So after annealing, basically we anneal 250, 350, 450. The size distribution did not really change a lot. They basically the medium part is about 50 nanometer. Okay, so even after annealing, they do not they more or less the same. But for the stacking fault, we can see before annealing, after annealing, they actually the density actually can reduce. Okay, so so at deposit film they have the higher concentration of this stacking fault or step facet, and they also have a smaller coordination number. Okay, for the copper surface. So here is a in-situ TEM images. We heat up to 650 degrees. Then you can see the second fault actually the density is reducing. Okay. If we look at the other images, we anneal about increasing the annealing temperature. We can see this twin stacking fault density also will actually change. Okay, and basically they can reduce all this density. So that means that annealing will actually make the reactivity of this catalyst, they actually reduce the reactivity. Okay, so then we have also tried to find out the exposed facet from this measurement. We found basically is a copper 111. The exposed phase or plane is copper 111 and 100. Okay, so they have a different plane. Then we have some simulation to tell us that there are other possibility for the coordination number. Okay, so this is the part we using the synchrotron X-ray to determine their crystal structure parameter. We roughly can find their coordination number, and we can also find a string, from all this fitting from this 5N element analysis. So basically, for the deposited copper, the coordination number is about 7.68. For copper foil, typically is 12. Okay, and then for the string, it's also agree with the our TEM analysis. About 1% of the tensile string is there. Okay, so this experiment from the synchrotron X-ray measurement, this analysis also supported that our deposited copper nanoparticle with a low coordination number with about 1% of the string. So then we actually put this material onto test, typically onto the full cell. 1M KOH, typical standard process. So for our case, this material is already can have 80% Faraday efficiency at minor 0.56 volt, and with the quite high current density 568 milliampere per square centimeter. So this result is already very encouraging. It's already compatible with most of the state-of-the-art copper material for C2H4. And then we looked at other annealed material. Of course, you can see the annealed material, annealed copper. The performance is not as good at deposited one. Okay, the deposited one is the highest performance in terms of the current densities, Faraday efficiency for C2, for C2H4, so on. Okay, so that also supported our, saying that the material, if you have tensile strength, higher the better, lower coordination number, the lower the better. Okay, so this is also show you that kind of conclusion for different current density for C2, C2H4, okay, and for the current density without H2. Okay, so the at deposit one is perform much better. Okay, so now typically people have to use KOH or for neutral electrolyte, KHCO3, but they will eventually lead to formation of the carbonate and crossover. So eventually it will make them the stability of the device will not be that great. So we performed one experiment by proposed by Sargent group, Edward Sargent from Toronto University. So they actually use a strong acidic electrolyte. So we actually repeat that and in the similar condition. So for the C2, we can get about 40%, okay, for minus 1.2 volt. If for this condition, 1M H3PO4 with 3M Ki, okay, so basically same as the work for the acidic, strong acidic environment. So we can get about 48%. So that is already better than, I mean, in terms of the catalyst itself, the C2 Faraday efficiency is already better than Sargent that group. But the problem is if we are using acidic electrolytes, so the MEA is not going to work because of the membrane, so it's not going to work. So this process is very difficult to actually make it become particle. But if we do not use it, we will have this. If we do not use very strong acid, the carbonate formation will actually block the play, and then they will cause flooding and all this. Okay, so it will reduce the stability. So so for us, we actually think of a way that in the introduction, people mentioned that if you use pure water to flood it into the cell, occasionally you can actually reduce the formation or actually prolong the formation of this carbonate. So for us, we only use pure water. So this is thinking, if we just use pure water, no alkalis, no acidic, okay, just pure water. But if pure water for the MEA cell, it will not really work very efficiently. if we just use the anion exchange membrane. So therefore we have to enhance the high pH local pH value. So we have to use another membrane as well. We have to use this proton exchange membrane. So once we use these two membranes together, using the pure water, we can get a pretty reasonable good Faraday efficiency. If we look at that part, we have about 43% Faraday efficiency for about 300 milliampere. Okay, so there's some reason, you know, because of the OH, we have to the AEM to allow the exchange for the OH and PEM, allow the exchange of the proton, and then they have the formation of the hydrogen rather than form this carbonate. Okay, so therefore we can actually still there'll be no crossover problem, and at the same time we can get pretty reasonable C2H4 Faraday efficiency. Okay, so so for total Faraday efficiency, you're talking about 66%. And for the C2H4, we get about 43%. So that is considered pretty good result in terms of the catalyst, in terms of the C2H2 Faraday efficiency. Okay, so so if we put using 1 mole KOH, we compare with 1 mole KOH and pure water. So initially the Faraday efficiency for C2H4 is pretty good. Okay, but for longer term, the pure water is actually perform much better. Okay, because we don't have the problem for this crossover problem. Okay, so then we assembly this cell. We stack it into 6 this MEA cell. So this is an image you can see. So we have a monitor, you know, we have a Arduino try to monitor all this current voltage, because we are aiming for a very long time operation. So this is a whole setup, the wheel setup, we actually have it. So overall, the stability for our stacked 6 MEA cells stacked can be more than 1,000 hours. Okay, and for the C2H4, basically they maintain pretty high level, close to 50%. Okay, so because of a static cell, so we also improve the Faraday efficiency from about 43 to about 50%. And the voltage we use is about 25, and then at the time go by, we increase a little bit. So so this is a very encouraging results. If we look at this figure, talking about from the literature, the state-of-the-art Faraday efficiency for C2H4, typically they can only up to about 200 hours. Okay, it seldom can be beyond 200 hours. So we also included our work for the acidic electrolysis, you know, based on our cell. It's about 20-something%. If for the alkaline we can reach 80%. It's almost comparable with some of the literature or some of the state-of-the-art catalysts can reach 80%. Okay. If we use water, the Faraday efficiency is just in between some of the best and not so bad one. Okay, but we can extensively extend the stability. Okay, the lifetime. So that, I mean, in the long term, this process become much more practical, and we just use pure water. They will simplify a lot of problems later on. Even the CO2 purity is not very critical if we use water. Okay, because it would not lead to some other product. Okay, I think my time is almost up, so I'll just summarize. So finding a catalyst with low coordination number and high tensile strength is very important, especially for the selectivity for C2 or C2H4 production. And we created, we proposed a new approach, just use pure water, but we have to use anode exchange membrane and proton exchange membrane together, so that we can, enhance this transportation for the OH ion and proton. Okay, so eventually, this approach can overcome the problem for the crossover, and hopefully it can also lead to practical use, because the lifetime can be extended for practical use. Okay, for that I would like to thank the main contributor, Seljat here. He did most of the work, and then Ning Ning also helped in the some other simulation work as well, and some other group member. Okay, for that I will end this presentation. Thank you very much.
Okay, so thank you, personnel, for the inspiring talk. So now we have time for several questions. So for audience, if you have a question, you can type it in chat, or you can turn on the audio. So again, maybe I start with the first one. So because I'm not working on this field, I have maybe a senior question. So about the C2H4, the product. So it's a pure product, or we need to do the separation after we get it?
Yeah, it's a pure product. You can actually get it directly.
Okay, that's good. Thanks. First one, maybe you have a question.
Okay, Professor Lau, in one of your slides, and you show the in-situ heating TM experiment, and after heating, and you can see the particle size decrease significantly. Yeah, here.
No, the particle size did not really decrease. If you look at, for anneal for 450 degrees, so the F is still about 60.
No, I mean in your TM, you can, if you compare A and B, right?
All right. I think it's about the focusing.
Okay.
It's not exactly about the actual size.
Okay.
Yeah, because it's because the focusing is not the same, because of the drip.
Okay.
Okay, so any other questions from the audience? Okay, so if not, then we thank personnel again. And okay, thank you. And this will be the end of this morning session. And I would like to thank again for all the 5 speakers in this morning session. And in the afternoon, we have another speakers, and we'll start at 2 p.m. You are welcome to join.
Right, thank you.
Okay, thank you. Then we stop here for the time being.